Hey, this video is What a Drag Graphing by Mr. Thiel. Okay, what I have here is a table of just made up data. This is just data that I just made up, but it's probably something similar to what you may have for your the first part of the What a Drag experiment that we did, which was measuring static friction on different surface types. And so this is the graph of my data here. And the first thing that I've already gone through and figured out the averages and the actual force rankings as compared to my predicted force rankings. But now I need to figure out what the independent variable is and what the dependent variable is. So remember, the independent variable is the thing that we were manipulating and the thing that we knew before we ran the experiment. And so this, of course, is the surface type. Surface type is our independent variable because we changed our different surfaces, or sliding surface, excuse me, if you like. And then our dependent variable would be the variable that responds to what we manipulated, and it's the thing that we don't know before we run the experiment. So in this case, that is what we're measuring, which is in fact the static frictional force, or just static friction, which is a force, so it's measured in newtons. Okay, so now I go to the graph. We go to the graph and we have to place or figure out what goes on the x-axis and the y-axis. And unless we're graphing time, which we are not in this case, the x-axis will always be our independent variable. So in this case, the independent variable is our surface type, or sliding surface, if you like. Now we are doing a bar graph here, so we don't have to figure out the scale in the same way for the x-axis here as we would do for a line graph. Now when we figure out the scale for the y-axis, we will have to do that in a similar way. So remember, our surface types, we have wax paper, paper towel, fine sandpaper, coarse sandpaper, and bare tabletop. And I've drawn these blue lines here, which represent the beginnings of the bars I'm going to put on my bar graph. And make sure that you do separate the bars. They should not be touching each other, because this is not a histogram. We're working with different items, or completely different categories here, so we would keep them separated, not together, on our bar graph. Okay, so now knowing that our surface type is our independent variable and goes on the x-axis, we can also now assign our dependent variable to the y-axis. So our dependent variable, if you remember, was the thing we're measuring, which is static friction, which is a force, so it is measured in newtons. It's important that you put the quantity that we're measuring, the static friction, and also the units, which are in newtons. Now, to figure out the scale for our y-axis, which contains static friction, we do have to go and go through and figure the steps to finding scale that I've given to you in your steps to making graphs. So for static friction, we've got to go through these steps. So you have to figure out the minimum and the maximum of your data. So if we go and look at our data, we are looking at the maximum should be some number that's just above your highest data point. So our highest data point, and we're looking at the averages here, is 2.13. So that's our highest data point. So our max would be 2.2. We just round up just a little bit, 2.2. And our minimum, I told you, should always be 0. So the minimum is 0. And now to calculate the range, what we do is we subtract the minimum from the maximum. So we do that, and we get 2.2. So now what we have to do is go back to our graph and count the number of boxes. So I won't take the time to do that here in the video, but if you go count the number of boxes, you will get that we have 20 boxes on the y-axis. So what we would do is we divide our range by the number of boxes. So we take 2.2 divided by 20, and we get 0.11. And remember, now the last thing we have to do is we have to round that number up to the next number that's on the sheet that I gave you. Usually we're talking about some multiple of 2 or 4 or 5, and in this case we are just above 0.1, which would be acceptable, so we have to round up to 0.2. If you are right on 0.1, which might be true for some of you, then you can go ahead and use 0.1. That's okay. It should fit all your data. Okay, so then that we will go back to our graph. Whoops, already got that part done. So here we are, and we will fill in our numbers. So we write up the y-axis, we go 0.2 for each line, and we get all the way up to 4.0, and that is our scale for our y-axis. So now we return to our data table, and we have to graph for each of our surface types. We have to graph that we're going to graph the average static friction. So we have 1.25, we have 1.25, we have 1.38, we have 1.88, we have 2.13, and we have 0.68 for our 5 surfaces. So then we will return to our graph and place those bars on our graph. So I'll place the bar for wax paper, the bar for the paper towel, the bar for the fine sandpaper, for the coarse sandpaper, and for the bare tabletop. And then to make them easier to see, fill them in, and I'll even outline them. Okay, so now our bars are easier to see, and we're essentially done. But there is one last step here that we need to add, and make sure you don't forget, and that is to add your title. So we have the surface. The title that I'm choosing here it's really my x versus my y, my independent versus dependent variable. So I have surface type effects on static friction. So how surface type affects static friction, and that's our first bar graph. And yours probably will look somewhat similar, but should also be different and unique to your data. Alright, now I've decided to skip Table 2 and the second graph because it's very similar to the first graph, and go to Table 3. Table 3 is a little different because we don't have, well, it's very much the same, where the first two graphs are both about surface tension. This graph, or surface texture, not tension, excuse me, about surface texture. This graph is about loads, and it is not about surface texture and loads effect on sliding friction. So I decided to go and do this one because we do have a different dependent variable. But again, we need to determine our independent variable is the load. It's the number of blocks, and that is what we knew before we ran the experiment. It's the thing we were manipulating in the experiment. And so the dependent variable is the other factor. It's the factor that responded to the number of blocks that we put on that we stacked up, and it's the thing we didn't know before we ran the experiment. So that was the sliding friction, which we measured in newtons. So now we come to our graph, and we will write in our x-axis, which is the load or the number of blocks. And then I will mark out where my bars will be. So I have the first bar is just 1 block, 2 blocks, 3, 4, and 5 blocks. Again, the little blue lines are marking where my bars will start on this graph. And now we can also, because we have assigned our x-axis, and it's the independent variable, the load, we can also assign the y-axis as the dependent variable, which in this case was our sliding friction. And again, friction is a force, so it is measured in newtons. Okay, again, we don't have to determine a scale for the x-axis because it contains the categories, the number of blocks, and in a bar graph we don't have to determine the scale in the same way for that. But on the y-axis we do have to determine the scale for our dependent variable, the sliding friction. So for sliding friction, again, remember we have to choose a maximum and a minimum, and our maximum data point on the average is what we're graphing. That's 2.58, so we will choose a maximum just above that, which is 2.6. And our minimum, I've told you, should always be 0 for this class, and so we have 0. And then to figure out the range, we subtract the minimum from the maximum, so that gives us our range of 2.6. And we're using the same grid, so the number of blocks on the grid is 20 blocks. So to figure out to get to the point where we can figure out our scale, we have to divide our range by the number of blocks, which is 20. And so 2.6 divided by 20 is 0.13. Well, that is not a good number to use for a scale. It'd be a difficult number. So what we need to do is we need to round that number up to 0.2. 0.2 is a much more convenient number to use for our scale. So again, we come back to our graph and we will write in our scale numbers for the y-axis on the y-axis on the left side there at 0.2 newtons per line. So we write that in 0.2 per line all the way up, and just like our first graph, we're going to get up to 4.0, and that's where our scale should end. Okay, now from this point on we can start placing our bars on the bar graph. So for the first block, well, we'll go back just for a second. So for each of our surfaces, we are graphing the average. So we have 0.6 for one block, 1.08 for two blocks, 1.50 for three blocks, 2.05 for four blocks, and 2.58 for 5 blocks. So now we come back to our graph and we'll go ahead and put our bars on there. We have our bar for one block, 2, 3, 4, and 5 blocks. And to increase the contrast, make the bars easier to see, maybe make it look a little bit nicer, we'll color in our bars and outline the bars, and that is it, except for the one last step, which is to make sure that you put in your title. So here again we're looking at something to do with the independent variable, the x-axis, versus the dependent variable in the y-axis. So here I've written load effects on sliding friction. Okay, and that's an example of how to do 2 of the 3 graphs that you have to do for your lab. So I'd like you guys to work on finishing those and then hopefully turn those in at the end of class. All right, thanks.